Hi everyone, welcome to the second and final lecture of the Professor Govind Swarup Memorial Lecture Series by Professor Nissim Kanekar. Professor Swarup was a pioneer in radio astronomy and played a crucial role in developing the world-class research facilities for radio astronomy in India. To commemorate his outstanding contributions to the field, Professor Nissim gave an excellent talk last week which you can find on our YouTube channel. Professor Nissim currently works at NCRA-TIFR. He mainly works on astronomical studies of the fundamental constant evolution, galaxy formation and evolution, and understanding conditions in the interstellar medium of the Milky Way. His lecture today will be focusing on atomic hydrogen in high-redshift galaxies. Professor Nissim, over to you.
Thank you, Vivan. Right, so today I'm going to be telling you about atomic hydrogen in high-redshift galaxies. And as Vivan mentioned, last week I spoke about Govind and Govind's contribution to Indian radio astronomy, setting up, building telescopes, building groups. And today I will talk about, I will start with the reason for building his last telescope, the GMRT, the Giant Meter Wave Radio Telescope that you see in the background picture. And 40 years of work, which finally has resulted in the first detection of atomic hydrogen in high-redshift galaxies. And Govind, unfortunately, was passed away on September 7, 2020, but he knew of this work. He passed away before the paper was finally appeared in the journal. And so he's not with us, unfortunately, to actually see the result out here, but it was an important part of his work. The person that you see on the left over here is actually not a young Govind, despite the large smile and the glasses. That's Aditya Chaudhary, who is a PhD student at NCRA, and who did the bulk of the work that I'll be talking about in the second part of the talk. So this is the broad outline of the talk and also a broad timeline. The 21 centimeter line was predicted to exist in the mid-40s, and then it was detected finally in the 1950s. So I'll start with the 50s, and with the 21 centimeter line, I'll do a jump to the 1970s and tell you a little bit about the problem with the universe as seen in the 70s. The fact that there was a lot of matter missing in the universe. In the 1980s, paradigms changed, and I'll tell you how we moved from one paradigm to another. In the 1990s, the Cosmic Background Explorer satellite spelled the death knell for the hot dark matter cosmology. In 2002, the GMRT came online, and it was built in order to look for these massive galaxies in the early universe in their 21 centimeter line emission. In the 2000s, the development of the Hubble Space Telescope, the Keck Telescope, and the Very Large Telescope in the previous decade, in the 90s, meant that suddenly there were a whole bunch of observations happening of stars at high redshift. And I'll tell you a little bit about this and what we know about the evolution of the star formation in the universe. And finally, I'll segue to the return of atomic hydrogen in terms of probing the highest redshift galaxies. So that's a broad outline. I'll tell you where we hope to go in the next few years or so. So what is the 21 centimeter line? So of course the 21 centimeter line is a quantum mechanical transition. It corresponds to a jump that the electron does semi-classically inside an atom. And most of you will be familiar with the usual jumps from one principal quantum number level to another. For example, the Lyman-Balmer-Paschen series in atomic hydrogen, where, for example, in the Lyman series, the electrons jump from, say, n equal to 2 to n equal to 1. And those are just the principal quantum number jumps. The 21 centimeter line is very different from these. It's similar and different. What's happening here is that there is, of course, a transition from one energy level to another, but here the transition is within the ground state of atomic hydrogen. In the ground state, there are two possible orientations of the electron spin relative to the proton spin. In one orientation, the electron spin is parallel to the proton spin. In the other orientation, the electron spin is anti-parallel. And it turns out that these two orientations give you different energies. And so you can have a transition in which the electron spin goes from being parallel to the proton spin to being anti-parallel. And that transition happens with the emission of a photon at a frequency of 1420.4058 megahertz, which corresponds to roughly lambda 21.11 centimeters. And this is called the 21 centimeter line. Astronomers are not known for their originality in names, shall we say. So the fact that the wavelength is 21 centimeters gives you the name of the line. Now, going back to the Lyman-Balmer and so on lines, these are extremely strong lines. The way you quantify the strength of a spectral line is by what's called as Einstein A coefficient, the probability of a spontaneous transition per unit time. And the Einstein A coefficient of these transitions between principal quantum numbers, say in hydrogen, is about 10 to the power 8. So about 100 million per second. And so particles basically very quickly jump from one level to the other until they reach the ground state. And these lines are at ultraviolet or optical wavelengths, very strong lines. On the other hand, the 21 centimeter line is an extremely weak line. The Einstein A coefficient is 10 to the minus 15 per second. So it's 1 part in 10 to the 15. And what this means is that a hydrogen atom in the upper state will sit there for about 10 million years before transitioning to the ground state. And this makes the line extremely weak. The frequency, as I said, is 1420.4058 megahertz. But van der Hulst in 1944, after some prodding from Jan Oort, realized that the fact that there's so much hydrogen in the universe means that even though the line is weak, the fact that there's so much hydrogen means that it should be possible to detect the 21 centimeter line from the galaxy, from the Milky Way. And this was a very interesting idea. This is in the middle of World War II, towards the end of World War II, and of course the difficult times. But during these times, van der Hulst made this prediction. And 7 years later, the first 21 centimeter signals were detected by Eben Purcell at Harvard and Muller and Oort in the Netherlands, and shortly afterwards by Christensen and Heinemann in Australia. And this was the first spectral line in radio astronomy, and it was the harbinger of great things to come. Even as interesting, just 3 years later, in 1954, Frank Kerr and Heinemann came up with the first detection of 21 centimeter emission from outside the Milky Way, from the Large Magellanic Clouds. And that started a completely new field of tracing galaxies, tracing the hydrogen content of galaxies with the 21 centimeter line. So what can 21 centimeter do for you? The reason 21 centimeter is so important is that galaxies are made up of stars and gas, and the universe is about 75% of hydrogen by mass. Most of the universe is hydrogen, about 25% is helium, and everything else is less than 1%, much less than 1%. So hydrogen is the bulk of the mass in the universe, and 21 centimeter traces hydrogen. So that already tells you that 21 centimeter is a foundationally important line for understanding the universe. The second thing, though, is that galaxies are basically, if you like, I wouldn't call them black boxes. The life cycle of a galaxy involves the transition of atomic gas via some kind of cooling. So the atomic gas cools, it forms molecular gas, molecular hydrogen. The molecular hydrogen further cools, self-gravitates, and forms stars. The stars then go supernovae at some point, and the supernovae throw metals, things like iron, nickel, chromium, whatever, into the interstellar medium. And these metals cause further cooling of the gas, and the gas further cools and forms molecular gas, and forms stars, and forms supernovae. And so you can see that the life cycle is basically the conversion of atomic gas into stars, and back again via cooling. And a galaxy basically stops functioning as a galaxy. It dies, so to speak, once its atomic gas is completely exhausted. At that point, it can't form stars anymore, and the stars just basically slowly live their lives and die out. There's no gas anymore to form new stars. So if you want to look at a live galaxy, hydrogen is crucial. Atomic hydrogen is the primary fuel for star formation, and I will use the abbreviation H1 or HI for atomic hydrogen. I'll call it H1 from now on. And just to give you a picture of what galaxies look like in atomic hydrogen, I've shown a picture of this famous galaxy NGC 6946, a beautiful spiral disk galaxy. This from Renza Boomsma's PhD thesis. That's an optical image on the left, which shows you the stars. You can see these beautiful spiral arms going out. And next to this image on the right, you see this gigantic object, which is the same galaxy exactly on the same scale, but now in atomic hydrogen. And so you see that atomic hydrogen stretches out a much larger distance than the stars. In the central regions, of course, the hydrogen is much more condensed. It's much brighter, but the hydrogen goes out at least a factor of 2, and usually it's often a factor of 5 to 6 further than the stars. And that's the general picture we have of galaxies. The H1, the atomic hydrogen, is hugely extended. And unsurprisingly, that image that you see on the right is made with the 21 centimeter line. That is the primary tracer of atomic hydrogen in the universe. And in fact, the 21 centimeter emission strength, the strength of the signal, is proportional to the atomic hydrogen gas mass. We know the proportionality constant. And this says that if I want to measure the mass of a galaxy, I just need to, the atomic hydrogen mass, I just need to measure the 21 centimeter signal from that galaxy. And that's it. And this is in fact the only way to measure the atomic hydrogen mass of galaxies. And this has been used for 70 years now, since 1954, to measure the mass of external galaxies with telescopes like the Westerbork telescope, the Arecibo telescope, the Very Large Array, and the GMRT. What's the catch? The catch is the fact that, remember I said that the Einstein A coefficient of the 21 centimeter line is very low. It's 10 to the minus 15 per second. The line is really weak. And this means that this line is very hard to detect as the galaxy is further and further away from us, and especially hard to detect at cosmological distances. So at redshifts larger than, say, 0.2 or so, it's extremely hard to detect the 21 centimeter line. In fact, the highest redshift at which a single galaxy has been detected today is 0.376, and that's one galaxy. There are a few more galaxies at redshifts of 0.25 or so. Very, very hard to detect this line at cosmological distances from normal galaxies. So that's what 21 centimeter emission can do for you. So let's now jump to the 1970s. The other beautiful thing of 21 centimeter is that it's a spectral line. A spectral line is special because a spectral line can provide you with velocity information. A spectral line comes at a fixed frequency. But now let's imagine that the object, let's say the gas which is emitting the line, is moving towards you. If the object is moving towards you, the spectral line will be Doppler shifted to higher frequencies. It will be blue shifted, as the jargon goes, in wavelength. On the other hand, if the gas is moving away from you, the line will shift to longer wavelengths or lower frequencies, and the line will be redshifted. And so the motion of gas can be immediately determined by observing a spectral line like the 21 centimeter line. And this is extremely interesting because, for example, we know that galaxies rotate. So when a galaxy rotates, one part of the galaxy is moving towards you and the other part is moving away from you. The opposite side is moving away from you. So now if you make an image of the galaxy in the 21 centimeter line, one side of the galaxy will be blue shifted and the other side will be red shifted. And that's shown in the image that you see on the right over here, which is of a famous disk galaxy M33, a rather beautiful image by Brown and Thilker in 2004 using the Very Large Array. And you can see that on the left side of the galaxy, all the whole emission is blue, and it's color-coded by velocity. The right side is red. The left side is moving towards us, the right side is moving away from us, and the galaxy is in beautiful rotation. Now, when you have this nice rotation measurement, you can even nicer, you can measure how the rotation speed of the galaxy changes as you go further and further out from the center of the galaxy. You can measure how the rotation speed of the galaxy depends on radius, the distance from the center. And this is called the rotation curve. Now, if you have, let's say, gas in circular orbits, then Kepler's laws will tell you that the velocity goes proportional to the mass to the power half and the radius to the power minus half. So it's equal to roughly g, the gravitational constant, m by r to the half. And we know in galaxies, the visible mass, the mass that we see, both in stars and in gas, is mostly in the central region. Which means that when you go further and further out, there's not much mass in galaxies. And so the mass, once you go further and further out, the mass is not increasing. So the mass is roughly constant once you go to large R. And what this means is that if you look at this equation, if you go to large R, both g and m are constant, which means that the velocity should go proportional to 1 upon r raised to half at large R, which means that the rotation speed of a galaxy should decline as you go to large radii. And that's the prediction from fairly basic theory. What you see over here on the right, on the second figure, is a plot of velocity versus distance versus radius from a paper by Salucci in 2019. This is a modern image, and this is the same galaxy M33. And what you expect is shown in the dashed line that you see below, which is basically from the visible disk. You expect the rotation speed to increase steadily as the mass builds up, and then at some point you expect the rotation speed to drop. And that's just because beyond some point you're not building up much mass. And so you expect the rotation speed will basically drop and then keep declining like 1 upon r to the half. What you actually see is shown in these points, in the measured points over here. And the yellow points over here are from starlight, and those are from stellar measurements, H-alpha spectroscopy, and you can see things are rising, but you're not going very far with the stars. But then you see a bunch of white points at large radii, larger than about 20,000 light years, and those are from the 21 centimeter line. And you can see that way beyond the starlight, the 21 centimeter light is allowing you to actually measure the rotation curve out to nearly a factor of 5 more than the starlight, and the rotation curve is either flat or rising in this case. And this is what people found in the 1970s, that when you combined 21 centimeter maps and optical H-alpha spectroscopy, you got either flat or rising galaxy rotation curves. And Vera Rubin was one of the outstanding people in this field in the 70s. She actually started this in the early 70s, but only went a short distance out. And then Albert Bosma and Mort Roberts and company did wonderful work with Arecibo telescope in Westerbork. And then Vera Rubin came back with 3.6 meter optical telescopes and new instruments and pushed the measurements further and further out in galaxies. And they found fairly definitively that galaxies have flat rotation curves. So what does this mean? Why do flat rotation curves matter so much? They matter because, go back to this equation up here, if the rotation curve is flat, that means that the mass cannot be only in the central region. The mass has to keep increasing because V is a constant at large radii, which means that the mass has to increase proportional to the radius. That's the only way in which you can have the velocity going flat. And so what this is telling you is that there is some extra invisible mass that we don't see, which is of course, unsurprisingly called dark matter, which pervades galaxies and extends out to very large sizes. And in a very nice annual reviews article by Sandy Faber and Jay Gallagher, they made this comment at the end of the paper that it is our opinion that the case for invisible matter in the universe is very strong and getting stronger. This is 1979, just after Vera Rubin and Bosma's seminal work in the late 70s. So that was the picture in the 70s. What is the matter and where is it? What matter are we talking about over here? And that's when things started getting very interesting. So in the early 80s, late 70s, early 80s, people realized that there are two possible forms of this matter. And this dark matter could be either relativistic, what is called hot dark matter, or it could be non-relativistic, what is called cold dark matter, HDM and CDM, and there were a whole bunch of papers on this. In the early 1980s, late 70s to early 80s, hot dark matter appeared to match observations much better than cold dark matter. And what was even nicer was that, you need a particle, you need some kind of dark matter particle. And there was a particle available for hot dark matter, which seemed to fit everything. There was a candidate hot dark matter particle, and that is simply a neutrino. Neutrinos were known to exist, and a massive neutrino, which is relativistic, would be a perfect candidate hot dark matter particle. In fact, Ramnath Kaushik at TIFR and John McClelland demonstrated that if neutrino masses were about 30 electron volts, you could close the universe. That would be a perfectly good hot dark matter particle. And what was very interesting was that the hot dark matter model predicted that the first galaxies that would form in the universe would be supermassive. The proto-galaxies that formed, the first galaxies, would be gigantic objects, and then you would form smaller galaxies by breaking up these big galaxies into smaller pieces. So you'd form these gigantic galaxies at very high redshifts larger than 3, very early in the universe, and those big galaxies you would expect would produce extremely bright 21 centimeter signals from their atomic hydrogen. And Sunyaev and Zeldovich had predicted that you might be able to see the 21 centimeter signals from these very high redshift galaxies. On the other hand, with cold dark matter models, the galaxies were expected to be formed in a bottom-up fashion, small galaxies being formed first. So the galaxies at high redshifts would be tiny, tiny or small, much smaller than in the hot dark matter model. And then you would build up the bigger galaxies by merging of these small galaxies, and you'd only steadily build up these galaxies with bigger and bigger objects. And the small galaxies meant that your 21 centimeter signal would be quite weak. So as I said, in the early 80s, late 70s, early 80s, hot dark matter seemed to be doing really well. And the redshifted 21 centimeter line frequency is the rest frequency, 1420.4 megahertz, divided by 1 plus z. So if Z is about, let's say, 3.5, then the frequency to which the line is redshifted is 327 megahertz. So if you want to detect this line from the highest redshift galaxies, you basically need a very high sensitivity radio telescope operating at 327 megahertz. And this was the primary science goal for Govind's proposal for the giant meter wave radio telescope, the detection of 21 centimeter signals from these supermassive galaxies predicted in the hot dark matter cosmology. And that came out in 1984, just when hot dark matter was at its, so to speak, its peak, where everybody was saying that, okay, hot dark matter is the best thing since sliced bread, and we need to detect it. And this was a clean prediction. Hot dark matter says you must see these huge galaxies at very high redshifts. And fortunately, Govind designed the GMRT, Govind and his team designed the GMRT to be a very versatile instrument. He didn't just build it to cover 327 megahertz, he built it to cover 150 megahertz, 233 megahertz, 327 megahertz, 610 megahertz, and 1420 megahertz. And this enabled a wide range of science, not just 21 centimeter emission at high redshift. So they started building the GMRT. They got funding approval in 87, as I mentioned last week. And then they started building it in the 90s. Unfortunately, things were changing. And so while the GMRT was being built, Govind is not a person who would just sit back and wait for a telescope to be built. He wanted to do stuff. So along with Ravi Subramanian, who was an outstanding PhD student at the UTI group in the 80s, Govind started the first 21 centimeter searches from galaxies at redshifts of 3.4. Remember, the UTI telescope already had 327 megahertz receivers. And it was a very big telescope, not as big as the GMRT, but it was still pretty damn big. So Govind and Ravi started doing these searches, and they published a couple of papers, Govind and Ravi in 87, and then Ravi and Antaramaya in 1990, basically saying they didn't see anything at all. And that was unfortunate, but not entirely surprising. UTI was not a very powerful telescope. And then something strange happened in 1991, where Dwan Usson, Durga Bagri, and Tim Cornwell used a very large array, and they claimed an extremely strong 21 centimeter emission signal at a redshift of 3.4. And that signal, the VLA, is shown over here with Jodie Foster in the foreground. This is the movie Contact. And the signal that they saw is shown over here, and that's this kind of jump that you see at channel roughly 10 in their spectrum. So that is the signal. It's an emission signal. So there's a little bit extra signal at channel 10 than there is at neighboring channels. And this was the signal that they were looking for. And they said, wow, this is spectacular. And this has to be coming from a supermassive galaxy. And this was already a bit of a problem in the early 90s because hot dark matter was going out of fashion. Some of the data, or much of the data now was supporting cold dark matter, was going against hot dark matter. And in cold dark matter models, it is very hard to produce such a massive galaxy with such a strong 21 centimeter emission signal. So Govind and Kandu Subramanian, who was an NCRA and is now at IUCA, argued in an extremely nice paper in Nature in 1992 that the signal that Dwan Usson and company had seen was not likely to be from a single gigantic galaxy, but might be a statistical detection of the 21 centimeter signal from a collection of small galaxies. So maybe a protocluster was forming, and there were a lot of small galaxies in the field inside your beam, and what you're seeing is a collection of the signals from all these galaxies. And that was a very interesting idea, and as you will see, it is fairly prescient. And it turned out, sadly, that other people, Frank Briggs, for example, and Kerr Brown, tried to confirm this detection at redshift 30, because people were hugely excited by this. They tried to confirm this detection with other telescopes, Arecibo and Westerbork, and the detection was not confirmed. And it turned out in the late 90s, Dwan Usson discovered that this was a fake signal coming from the VLA waveguides from the transmission system that the VLA had set up. And that was bad news, but this is kind of normal in the sense that when you're pushing a telescope to do cutting edge science, problems do happen. And they were good enough to identify the problem somewhat later. And they said, okay, this signal is not real. And that is it. So why did hot dark matter die? Hot dark matter died first in the mid-80s from the early n-body simulations of gravitational clustering by Mark Davis, Carlos Frank, George Efstathiou, and Simon White, which showed that cold dark matter produced structures which looked more like the actual universe than hot dark matter. And so the early N-body simulations by the mid-80s already indicated that cold dark matter is more likely to be the right model. There were still debates happening. But the thing that really killed hot dark matter was the Cosmic Background Explorer, COBE, which basically produced results in 1992, and that is observing the cosmic microwave background and the anisotropies in the microwave background, which come from a redshift at which matter and radiation decouple from each other, a redshift of about 1100. The anisotropies are very different in hot dark matter and cold dark matter. And COBE basically measured the amplitude of these anisotropies, and COBE definitively ruled out hot dark matter. You basically would not form galaxies at redshifts of 3 with the amplitudes that you were getting with the COBE signals. And so by the early 1990s, 1992 or so, it was clear that hot dark matter was dead. By the late 1990s, with the Type 1a supernova measurements, the standard cosmology had become the lambda cold dark matter model, lambda standing for the dark energy, what is called dark energy today, or the cosmological constant. And this is a model which is a slight variant on cold dark matter, but the broad picture of lambda cold dark matter is the same as cold dark matter, namely that there are small galaxies at high redshifts. They have individually very faint 21 centimeter signals, and you build up bigger galaxies by the mergers of these small galaxies. And so that basically meant it is going to be very, very, very hard to detect 21 centimeter emission from individual galaxies with the GMRT or with any telescope that was being built at the time. And so then Govind, again, while the GMRT was in the process of building, Govind realized that hot dark matter is going down. And so then, in order to detect individual galaxies and study galaxies in 21 centimeter, you need an even bigger radio telescope. And so in 1991, Govind and Peter Wilkinson independently proposed a much, much bigger telescope than the GMRT, much bigger collecting area, much higher sensitivity, which Govind called the International Telescope for Radio Astronomy, the ITRA, and Peter Wilkinson called the Square Kilometre Array, the SKA. And I'll tell you right at the end about the SKA, very briefly, I'll tell you at the end of the SKA today. So that was proposed in 1991, and we have still not come very close to building it as yet. So at the end of the 90s, hot dark matter was gone, gigantic supermassive protogalaxies were gone, 21 centimeter signals expected to be extremely weak and basically not detectable at high redshift from individual galaxies. And so that was kind of depressing, but of course the good thing was that the GMRT had been built to do all kinds of science. And so when the GMRT came online in 2002, there were a whole bunch of other things that the GMRT could do and did right away. Although it couldn't do its primary science goal, at the time when the proposal came in. So what happened? So that was the GMRT. So the GMRT has these 30 antennas, which have a diameter of 45 meters. And I mentioned that it's built with a mesh, with this smart concept. And it's got two polarizations, and it's a Y-shaped array. It's got 14 antennas in this 1 kilometer central square, separated by a few hundreds of meters, and then it's got 16 antennas in 3 arms of the Y. And the separation, the longest separation between two antennas is about 25 kilometers. So with the GMRT, you can basically synthesize a telescope of effective size 25 kilometers via the principle of radio interferometry, and that's the game with the GMRT. As I said, it's got 5 frequency bands, 150 megahertz, 233 megahertz, 327 megahertz, 610 megahertz, and 1420 megahertz. And the 610 megahertz band is the important one for the rest of this talk, and that corresponds to a redshift of about 1.4 for the 21 centimeter line. 327 megahertz is a redshift of 3.4 for the 21 centimeter line. And you can immediately see from the image on the left over here, which shows a bunch of summer students next to the GMRT antenna, that the GMRT dishes are big. These are normal sized summer students. They were not chosen to be particularly small. And the GMRT kind of towers above them. And that's just one dish. And there's 30 such dishes. And you see a bunch of them on the right over here with the hill of Narayangarh in the background. And as I said, the GMRT has spectacular sensitivity. But unfortunately, in lambda cold dark matter, it's not enough to detect 21 centimeter emission from the highest redshift galaxies. So this is bad news. But you can do a whole bunch of other science with it, and that's what people started doing in the 2000s once it came online. So what happened? In parallel with the building of the GMRT, a bunch of big optical telescopes came online in the 1990s. First, there was the Hubble Space Telescope, which of course is in space, and the Hubble HST had problems with its mirror, and those were fixed by about the mid-90s. The Keck telescope came online also in the early 90s and was functioning wonderfully by the late 90s. And the VLT came on. The VLT is a very large telescope. It's 4 telescopes in Chile. The Keck telescope is 2 telescopes on Mauna Kea and Hawaii. And the Keck telescopes are 10-meter class telescopes. The VLT is 8-meter class telescopes, 4 telescopes 8 meters in diameter. And the Hubble Space Telescope is only 2.4 meters in size, but it's in space. It's above the atmosphere. So it's wonderful for seeing really faint things without the atmosphere corrupting your vision. So that was spectacular optical instruments, which meant that you can see the stars from galaxies much, much, much better. But what was also interesting was that in the late 90s, Chuck Steidel and collaborators pioneered a bunch of new techniques to pick out star-forming galaxies at the highest redshifts. And this really changed the field. Until then, in fact, the highest redshift objects tended to be radio galaxies. So, for example, in 1999, Will van Breugel and collaborators found the highest known redshift object at that point, which was 5.19. And today we know many galaxies at redshifts larger than 8. And they've all been picked out with optical observations. And those have come starting from the work of Steidel and collaborators in the late 90s and early 2000s. So what did this result in? This resulted basically in thousands, if not millions, of star-forming galaxies detected at redshifts between 1 and today about 9. Redshifts of 1 to 6, many thousands of galaxies. Redshifts of above, let's say, 7, 7.5, not that many. Still in the tens to over 100 at redshifts larger than 7. But out of redshifts of 6, tons and tons of galaxies. And so what people did was that, starting in the late 90s, but especially from about 2005, people plotted the star formation activity in galaxies, which is basically the star formation rate density. How actively a galaxy is forming stars in the universe as a function of redshift. And what they found, and these are all individual measurements, what they found was that at very early redshifts, which is very early times, star formation activity in galaxies is relatively low. Star formation activity in the universe is low, and it slowly rises. And this is basically galaxies are forming, gas is flowing to the center of galaxies and forming more and more stars. And by about 11 billion years in the past, or redshifts about 3, the star formation activity is fairly high. And then for about roughly 3 billion years, up to redshifts of 1, star formation activity is about flat. Things just proceed the galaxies are forming stars at roughly a constant star formation activity. And then suddenly at redshifts below 1, star formation seems to slow down. And the star formation activity declines. And it declines by about a factor of 10 from redshifts of 1 to the present epoch. So today, galaxies are forming stars much less than they formed at redshifts of 1. And in fact, this epoch between redshifts of 1 and 3, about 8 billion years ago to about 11 billion years ago, is called the epoch of galaxy assembly. If you look at stars in the universe today, about half the stars in the universe today were formed during this period, redshifts of 1 to 3 or 8 to about 11 billion years ago. That's the epoch of galaxy assembly. So star formation in galaxies, the star formation activity, was about 10 times higher between 8 and 10 billion years ago compared to today. We know this from data. So this begs the question, why did the star formation activity slow down? What happened? And really, the only way to understand this question is to look at the fuel for star formation. Something must have happened to galaxies at redshifts of about 1, because of which star formation slowed down. And the way to probe this is to measure the hydrogen mass in early galaxies, because that's the fuel for star formation. But the problem, of course, is that to measure the hydrogen mass, you need to use the 21 centimeter line. And this is hard, because 21 centimeter, as I said, is really weak. How do you detect this line at even redshifts of 1 with today's telescopes? And that is the problem that one has to address. And so it is known it's very, very, very hard to find 21 centimeter from individual galaxies, but there's one way of increasing the sensitivity. You can do what is called 21 centimeter stacking. And this kind of goes back to Govind and Kandu Subramanian's idea that the original signal of Usson et al. Could be a statistical detection. It could be a signal from a collection of small galaxies. And so that idea of the signal went away, that signal was not real. But what if you knew the positions and redshifts of a bunch of galaxies within the field of view? What if you had a field of view in 21 centimeter, and now you know there are a bunch of galaxies there, and you know the redshifts, and you know the positions. So the left image over here shows a 21 centimeter image at some redshift. And there's nothing, it's just noise. You don't see any signals at all. The right image shows the same image, but now you know that there are galaxies at these positions in the image. Now, can you use this information to somehow increase the strength of the signal? Remember, these positions are from optical imaging and spectroscopy. You know the positions of these galaxies from optical imaging and spectroscopy, and now you go and make a 21 centimeter image of the field. And what Jairam Chengalur and collaborators and Martin Zwan independently realized in about 2000 2001 was that you can basically add the 21 centimeter signals from these multiple galaxies if the galaxy position and redshifts are known. And by adding these signals, you'll basically increase the strength of the effective signal, and this gives you average information about the galaxies. So let's look at what this means. What you do is that you need to align the 21 centimeter signals from each galaxy. So what I'm showing you over here in the movie on the left, made by Aditya Chaudhary, is that you have all these galaxies. You basically move these galaxies, you take the galaxy, move it to the center of your effective image, and add the signal. What I'm showing you on the right is the stacked signal on adding galaxies, and what's shown in the top right corner is the number of galaxies that's been added. And you will steadily see a signal being built up in the center of this stacked image as you add more and more galaxies, and that is the game. So now you will see the signal steadily building up, and you kind of see a faint thing starting to appear over here by the time you hit about 50 galaxies. And as you go along, the signal will get brighter and brighter. Of course, the more galaxies that you have, the more your signal will get high. And of course, this means that you need to accurately measure the positions and redshifts for a very large number of galaxies within the telescope field of view. And so obviously you will benefit if your telescope field of view is big, because then there might be more galaxies in there. But also you need to have optical spectroscopy done earlier so that you know exactly where the redshifts are. Because the galaxies at different redshifts will have the 21 centimeter line at slightly different frequencies. And now in order to stack these together, I need to stack each redshift separately. So this shows a stack of about 99 galaxies over here. And after stacking 99 galaxies, you can just about see a faint signal that was not visible initially. In reality, at a redshift of 1, you'll need to stack far, far, far more galaxies than 99. But this just demonstrates the technique that if you stack a lot of galaxies, you can dig out the signal from the noise, and this will allow you to actually probe the average properties of this population of galaxies. So that is the idea behind this whole thing that we're trying now. And so it turned out that there was this wonderful survey called the Deep 2 survey done by Sandy Faber, Mark Davis and collaborators with the Keck telescope, which gave you positions and redshifts for about 15,000 galaxies and redshifts of 0.75 to 1.4 in 7 regions of the sky. And so this shows 2 of the Deep 2 of the Deep 2 fields, which have 5 of these regions, and there are about 2,000 galaxies in each of these fields. The red circles on these fields show the size of the GMRT beam. And so basically, all the blue region over here, all the orange region over here, all the green region over here, and the blue and orange regions here are sitting within the GMRT beam, which means that the GMRT is seeing all of those galaxies at one shot. With a catch, it's seeing all the galaxies, but can it cover all the frequencies? So we'll come to that in a second. But this redshift range is really interesting, because remember I said that the star formation activity starts declining, as you can see on the right side plot over here, at a redshift of about 1. So this redshift range covers the the end of the epoch of galaxy assembly, 1.4 to 0, and it also covers the start of the decline of star formation activity, redshift of 0.75 to 1. And so this redshift range is interesting to understand why did star formation activity decline in the universe. And so that shaded region over here marks the redshift range that the Deep 2 survey covers. And so this makes it a very interesting target sample, if you like, for a stacking observation. What is the problem? The problem is that the original GMRT bandwidth was only 32 megahertz of the raw GMRT. And remember I said that the 21 centimeter line is at a frequency of 1420.4 megahertz. And for an object at some redshift, I need to divide 1420.4 by 1 plus the redshift to get the observed frequency. And it turns out that a 32 megahertz bandwidth will only let you cover a small number of galaxies of this large redshift range with one frequency setting. I will need to do multiple frequency settings, which means I have to carry out multiple observations to cover that entire redshift range. And that is really hard. I mean, your observing time shoots up. And so this was the problem with the original GMRT. And so what we did about 5-6 years ago, along with Shiv Sethi and Dwarkanath from the Raman Research Institute, we tried to stack the 21 centimeter signals from the galaxies in the Deep 2 fields using the old GMRT. And we basically could cover 850 galaxies in 4 regions. So about 250 galaxies, 220 galaxies in each region. And that's all we could do with the bandwidth that we had at that time. And that gave us an upper limit on the 21 centimeter signal. And that upper limit basically placed an upper limit of the average mass of the galaxies in the epoch of galaxy assembly at redshift of about 1.2. That's the best that we could do at that time. You would have needed much more observing time to do much better than that. And then the upgraded GMRT came along. The upgrade was finished in 2017, and the upgraded GMRT gave you a bandwidth of 400 megahertz. The 400 megahertz meant that now suddenly we could cover this entire redshift range going from a redshift of 0.7 to 1.4 in one setting. And that was spectacular. So we had new receivers which let us cover this whole frequency range in one shot, and we had this new correlator which let us correlate the entire bandwidth in one shot. And this meant that in one shot we could cover 11,000 Deep 2 galaxies in 5 sky regions. Instead of 200 galaxies that we covered earlier, we were now covering 2,000 galaxies at one shot. And that completely changed things. And so Aditya stacked about 7,500 of these 11,000 galaxies, which were clean, which had no interference, no problems. And that resulted in the signal that you see on the left over here, where the contours and the red region show the signal that we detected. And this spectrum over here on the right shows the emission signal that we saw from these 7,500 galaxies. And this was spectacular because this was the first measurement of hydrogen mass from the epoch of galaxy assembly at an average redshift of about 1. So what we got was the average hydrogen mass of these 7,500 galaxies at a redshift of 1. What we also got was a measure of the star formation rate of these galaxies. And so now we could divide the star formation, the hydrogen mass by the star formation rate. And that will tell you how long can the hydrogen mass fuel the star formation activity. And it turns out the hydrogen mass can fuel the star formation activity for only about 1 billion years. 1 billion years is a very short time, and that's roughly the period, as you can see over here. This is the time scale over here. So from redshifts of 1, the hydrogen mass in galaxies could fuel star formation in those galaxies for only about 1 billion years, after which star formation would have to slow down. And this basically explains the decline in the star formation activity at redshifts below 1. There just wasn't enough atomic hydrogen to fuel the star formation activity, so galaxies started slowing down in their star formation activity. And so that nailed the problem, so to speak. And so that's what we got last month in October. The work was, of course, done in 2019, but finally was published in 2020. So where do we go from here? The next step, of course, is, and this actually I should mention that, so we told Govind about this last year when we detected it, and Govind, of course, was super excited But after a few days, after the excitement, we chatted a bit about it. His first question was, what next? And that was Govind's really. It was really about, okay, you've gotten this, so now what? You have to do the next thing. You don't just sit back and say, okay, we've gotten something which is exciting. You push to the next piece of science, the next frontier, so to speak. So the first thing that we're doing now is to characterize the hydrogen at redshifts of 1 in an even more detailed way by much deeper observations. So what we're doing now is that we're doing a 500-hour observation of the same deep 2 fields, covering now about 11,000 galaxies, all of the 15,000, but with about 11,000 that we could use. And what we see over here is the results for 11,000 galaxies with 250 hours of data. The last 250 have just been taken and are being analyzed as we speak. And you can see the signal is much, much, much stronger. It's now about a 5.5 sigma result. And you can see in the spectrum also the signal is very, very clear now. These black dashed line curves are the are the errors in the signal. And you can see that the signal is very clearly detected. That's one. And so we expect that by about the end of this year, the start of next year, we should be able to, in fact, break up the signal into 2 halves and measure the average gas mass at redshifts of about 1.2 during the epoch galaxy assembly, and also at a redshift of about 0.8, 0.9 after the epoch galaxy assembly, and compare these two. And that's the plan for the next few months. The next step really is to push to even higher redshifts of 2 to 3, using the GMRT band 3 receivers, 300 to 500 megahertz, and push to the peak of the epoch galaxy assembly, this redshift range, 10 to 11 billion years ago. And we started this project now, and we'll be taking data on this from around January or February next year. And we plan to push, we'll be taking about 200 hours of data to start with next year, and with the hope to detect 21 centimeter emission from galaxies at this epoch, right at the peak of the epoch galaxy, at the peak of star formation in the universe. The next step, probably in the next few years, is to detect individual galaxies via ultra-deep upgraded GMRT observations. And that will require 1,000-hour integrations on single fields, which will be extremely challenging, but which is the next big step in the field. We are also planning or talking about building an expanded GMRT, what we call the eGMRT, and case studies for this are currently going on. And of course, in parallel, the Square Kilometre Array is underway, so to speak, in South Africa and Australia. And India is very much a part of the Square Kilometre Array. It's a partner country in the Square Kilometre Array. And NCRA is the nodal organization of the SKA India organization. So this is these are the next steps over the next, I would say, 5 years or so. We expect to definitely characterize H1, atomic hydrogen, in the the sample of galaxies at redshifts of out to 1.5 in a detailed way. We intend to detect atomic hydrogen in galaxies at redshifts of 2 to 3 at the peak of galaxy formation, of star formation in the universe in the next couple of years. And then we intend to detect individual galaxies either with huge observations with the UGMRT or with the next generation telescopes, the eGMRT and the Square Kilometre Array. So to summarize then, I hope I've convinced you that in order to understand galaxy evolution, you must understand both the stars and the gas. And 21 centimeter emission is foundational because it allows you to measure the hydrogen mass of galaxies, atomic hydrogen mass, and this is the primary fuel for star formation. The GMRT was originally designed to detect 21 centimeter emission from the massive, supermassive proto-galaxies expected in hot dark matter. Sadly, Kobe killed hot dark matter, and the standard cosmology today, lambda cold dark matter, predicts smaller galaxies at high redshifts, and it's very hard to see their signals. The 21 centimeter stacking allows you now to combine the 21 centimeter signals from many galaxies that are within your telescope field of view and measure their average properties. And with the upgraded GMRT, Aditya Chaudhary and our group has finally made the first detection of 21 centimeter emission at very high redshifts of 1, and we find that the hydrogen mass is sufficient to sustain star formation for only about 1 to 2 billion years. And this provides an explanation for why star formation activity in galaxies declined precipitously at redshifts below 1 after the epoch galaxy assembly. The next steps, of course, are to do a detailed characterization of galaxies, of hydrogen in galaxies during the epoch galaxy assembly, and push to even higher redshift 2 to 3. And we hope that in the next 5 years or so, we will actually detect individual galaxies with ultra-deep GMRT observations and the Square Kilometre Array. So that's where we hope to go. But I would like to say a couple of things about Govind himself now at the end of this talk. So of course, Govind's passing on September 7, 2020 is really in metaphorically at least, sunset for the GMRT. And Govind was an absolutely wonderful designer and builder of telescopes. He had all kinds of outstanding and interesting, innovative ideas. But something that Govind was, I would say, even more special for. There are many people who build and design telescopes. Govind was special in one important light, in that he actually built groups, he built people. And that is much harder to do. And he built a research culture. And so that, I think, is his most outstanding legacy. And although Govind is gone now, we hope to carry on his legacy over the next decade or more, using outstanding telescopes to do cutting-edge science and continuing to build the best telescopes in the world. Thank you.
Shall we take questions now, sir?
Yes, of course.
So the first one we have is, what exactly was wrong with Subramaniam and Swarup's Nature 1992 proposal of the 21 centimeter line from a host of small galaxies?
Oh, okay. So there was nothing actually wrong with it. So the thing was that they were trying to explain the signal that you see over here, right? So they were trying to explain one-Usson signal, and the problem was that signal went away. So the idea was perfectly okay, that maybe if the signal was real, that idea was reasonable. The problem was that the signal itself went away, and so then the explanation went away along with the signal. So there was no problem with the explanation. The problem was that the signal was not real.
Okay, thank you, sir. The next one we have is, why does the star formation rate rise and fall, and what determines the redshift at which it is maximum?
That's a very good question. So the star formation rate, so in order to form stars, you need to have a lot of gas in galaxies. And you need the gas to cool. So gas has to flow into galaxies, and then the gas has to cool and form atomic hydrogen, and then the gas has to cool further and form molecular hydrogen, and then the gas can form stars. So all of this takes time. You need to build up enough cold gas in galaxies before you can form stars. And that process is basically happening over here. So the first galaxies which condense out of the universe is expanding, and galaxies are forming via gravitational clustering. And the first galaxies probably formed at a redshift of about 20, 25 or so. And these are just, if you like, dark matter and gas. At some point, the gas starts to cool, and that gas becomes cold enough that you can actually self-gravitate, or the gas is self-gravitating, and that will form the first stars. Those first stars will take some time to go supernova, hypernova, and they will chuck metals into the interstellar medium of these early galaxies. Those metals will cause cooling to happen, and that will cause more gas to cool down and become and condense, and that will form the next generation of stars. All this takes time. So that process of cooling and building up more and more stars, which cause more and more metals to flow in the stellar medium, is what you're seeing over here. This, from redshifts of about 8, up to which we have the current best measurements, there just wasn't enough. There weren't enough stars. There wasn't enough. The metallicity was low. The number of metals were in galaxies was low, and we steadily built up stars in the universe from redshifts of about 8 to about redshifts of 3. So the formation of stars, of increasing the star formation rate, is completely coupled to the buildup of gas in galaxies and the buildup, more importantly, of cold gas and metals in galaxies. And that just takes a lot of time. And so redshifts of 3, about 2 billion years, 2.5 billion years after the universe started, was about where you hit the peak of star formation activity in the universe. Because by that time, there were enough metals in galaxies. And so there was enough, you could cool gas very efficiently and then form stars very efficiently.
As a follow-up to that, sir, can the redshift at which the star formation rate is maximum be expressed only in terms of the cosmological parameters?
Well, it's more complicated than that. It's not really a mathematical formulation. You have to worry about the physics of star formation. So you have to worry about baryonic processes, which are much more complicated than cosmological parameters. So I would say a brief answer is no, but I think you can't predict the redshift at which this would happen now. Once you have if you had information with the cosmological parameters, if somebody gave you perfect information about cosmology, you could predict at roughly what epoch the first galaxies would form, and roughly at what epoch the star formation activity would peak. But the second prediction is much harder because that prediction will depend on the complications of gas physics. And gas physics is much less well known than, for example, gravitational physics of dark matter. So you can predict things roughly, but not I don't think you'd be able to, for example, make an accurate prediction which says that, oh, this will happen by redshifts of 3, just because the gas physics is complicated. So the observations are really important over here. They have told us what star formation activity is like in the real universe.
So, other than the star formation rate, what else can we determine or infer from the 21 centimeter emission lines?
Oh, okay, so you are not determining the star formation rate from 21 centimeter. You're measuring the hydrogen mass. The star formation rate is being determined from optical studies of stars. The 21 centimeter line is simply giving you the hydrogen mass in galaxies, which is the fuel for star formation. So our observations are basically explaining why the star formation rate declined by measuring the hydrogen mass in these galaxies. So 21 centimeter can be used for a range of things besides hydrogen mass. It can be used, as I said, to measure the kinematics of galaxies, the rotation of galaxies. And so it can be used to infer dark matter. And that was done in the 70s for nearby galaxies. It can be used to do something else that I do with it is fundamental constant evolution. If you compare the 21 centimeter redshift of a galaxy with, for example, the hydroxyl redshift of the same galaxy, or the redshift of the galaxy via atomic carbon lines, you can actually test for changes in the fundamental constants of physics with the 21 centimeter line. You can measure the temperature of gas in galaxies by doing 21 centimeter absorption studies towards quasars. So 21 centimeter is a very versatile probe. And of course, 21 centimeter is going to be used extensively now in the next 10 years or so to look at what is called the epoch of reionization, which is the last phase transition in the universe, which happens at redshifts of, say, between about maybe 12 and 6. It ends by about redshift of 6. And the universe, the intergalactic medium, was predominantly atomic hydrogen at that point, at redshifts of, say, 8 or so. And the 21 centimeter signal from these epochs would be quite strong, because the entire universe, not just galaxies, was atomic hydrogen, neutral atomic hydrogen. And so telescopes are being built to look for this signal. For example, the low frequency array LOFAR in the Netherlands, the MWA, the Murchison Wide Field Array in Australia, the HIRA telescope in South Africa, have been built primarily to look for this 21 centimeter signal from the epoch of reionization. And the idea is that this is the last frontier of cosmology. That if you can understand the 21 centimeter signal, you can actually get a huge amount of information about the universe, about the cosmological parameters and the universe by observing this 21 centimeter signal from the epoch of reionization. And that will happen in the next, I would say, 5 years or so. There have been claims already of a detection at much higher redshifts, but the jury is still out on those claims.
Coming to the final question, sir. Especially now with emerging new fields like gravitational wave astronomy, do you feel that radio astronomy or in general electromagnetic astronomy will lose out on its importance in any way?
No, absolutely not. So all the gravitational wave work is wonderful, right? It's just absolutely spectacular. But think about that image that was made last year of gas around the black hole, right? With the Event Horizon Telescope.
Yes, sir. Yeah.
Right? So that's the Virgo black hole. That is absolutely spectacular. That is made with radio telescopes, with millimeter wave radio telescopes. And so I think what will only happen, it's like this question is like saying that once radio astronomy became important in the 40s, 50s, 60s, did optical astronomy die out? It didn't. We just learned much more about the universe. So what gravitational wave studies will give us is one more tool to understand the universe. Electromagnetism is still going to be a fundamental tool, probably the fundamental tool, and gravitational waves will combine with electromagnetism to give us much, much, much more information about the universe. That's wonderful. I mean, we'll get different ways of understanding the universe, which we didn't have before. So no, electromagnetism is alive and well and kicking, and will continue to be alive and well and kicking for a while to come.
Thank you for that very intriguing perspective. And also the talk, in my opinion, it was a very perfect fitting conclusion to this lecture series.
Thank you.
A perfect note to Professor Swarup.
Thank you.
Yeah. We don't have any more questions, sir. Thanks a lot for your time.
Great. Yeah. Goodbye then.
Yeah. Goodbye, sir. Thank you. It was great having you with us.
A pleasure.